Okay, with some prompt engineering, we can have ChatGPT or Grok produce us unique questions for the actuarial exam. This question corresponds with the continuous distribution section. Here, we're asked to find the minimum and maximum using uniformly distributed random variables. We're given X, Y, and Z have uniform distributions over intervals 2 to 5, 1 to 4, and 0 to 3, respectively. And again, we're given that they are independent, which will be important. The first thing I want to do is write down our information again and expand on that. So with X, I'm going to say it's uniform from 2 to 5. And then we know that the probability function for X is, well, very generically, it's 1 over B minus A, which means that we have 1 over 5 minus 2, or 1/3. Same thing for Y, uniform on the interval 1 to 4. The probability of Y is going to be 1 over 4 minus 1, which gives us, again, 1/3. And the same goes for Z, interval from 0 to 3. Our probability function is also 1/3. So now we have our three functions for the individual random variables. Now let's take a deeper look at what the actual question is asking us for. So the first part asks us, what's the probability that the maximum of X, Y, and Z, that value is less than or equal to 3.5. The less than or less than and equal to doesn't really matter, since in calculus, the endpoints are automatically contained in an integral, but we're going to go ahead and keep it that way. The second part of the question asks us, for these three variables, what's the probability that the minimum is less than 1.5? So I think the best way to think about this is to look at what do the maximum and minimum contain. So in the case where it's asking the maximum being less than a value, we know that all of the X, Y, and Z values must be less than 3.5. Because if any one of those cross it, that will be the maximum value. So we can just say for max, all X, Y, Z must be less than or equal to 3.5. Now, with the minimum being less than 1.5, it's asking us for at least one of those variables being less than that 1.5 value. And that's going to make it a lot more difficult to solve. But we can cross that bridge when we get there. Let's solve the maximum first. I will rewrite this. Now, we can say that this is equal, since all values must be less than 3.5, it's equal to the probability that X is less than 3.5 and Y less than 3.5 and Z less than or equal to 3.5. These intersection symbols will reflect the and that I'm using, since when they all intersect, it must be that they all and they are all having that value or following that rule. Now, because we're given that the variables are independent with our rules for intersections, we can then rewrite this to say that the probability that x less than 3.5 times the probability y less than or equal to 3.5, and we multiply the probability that z is less than or equal to 3.5. This also equals the probability that the maximum of those three values is less than 3.5. So now all we need to do is solve for each of these individual probabilities. So probability that x is less than or equal to 3.5, we know that will be an integral from 2, the lower bound of its interval, to 3.5. And we integrate that over its probability function, dx, 1/3 dx. And that'll give us x over 3 from 2 to 3.5. This simplifies down, 3.5 over 3 minus 2 over 3 gives us 1.5 over 3, easy 0.5. We do the same for y. We integrate it from its lower bound, which is 1 to 3.5. And it has the same probability. So x over 3 from 1 to 3.5. 3.5 over 3 minus 1/3 will give us 2.5 over 3. And that's equal to 0.8333 repeating. Lastly, we're going to do this for z. Now, z is unique because the interval we're given is from 0 to 3. So the probability of it being less than 3.5 must equal 1. If we do the integral, we're forced to do the entire range. And with a probability, if you're looking at an entire range of the interval, it's going to equal 1. But we could just do the math. 3 over 3 minus 0 over 3, it's 1. So here are our three values that we can plug back into this product we have here. So we have 1 times half times 0.8333 repeating. This gives us 0.4167. So we know that the probability that the maximum of x, y, and z is less than or equal to 3.5 is about 41.67%. Now we want to solve for the minimum. So again, the minimum, we cannot at this point use our independence rule just to plug and chug. But what we can say is that this is equal to 1 minus the probability that the minimum of x, y, and z being greater than 1.5. These values will be equal since this is the inverse. Now, the probability that the minimum of these three values being greater than 1.5 is all encompassing. So again, this is saying that all x, y, and z must be greater than 1.5 in this situation, which allows us to solve the problem using that product of all of the variables being multiplied by each other. So we can say that this portion right here is the same as the probability of x being greater than 1.5 times the probability of y being greater than 1.5. times the probability of z being greater than 1.5. Now we need to figure out the probability value for each of these. Again, probability being greater than 1.5, we have the range from 1.5. Well, so for x, because the interval is from 2 to 5, similar to z in the former part where we were looking for the maximum, it's all encompassing. So this would be from 2 to 5 of 1/3 dx, which is equal to 1. Now we do y being greater than 1.5, and that interval is 1 to 4. We can actually do some math. So we get x over 3 from 1.5 to 4, 4/3 minus 1.5 over 3 gives us 0.8333 repeating again. Lastly, probability that z is greater than 1.5. From the 0 to 3 interval, we have 1.5 to 3. X over 3, 1.5 to 3. 3/3 minus 1.5 over 3 gives us half again. And we have the exact same product. Half times 1 times 0.8333 repeating gives us 0.4167. But remember, what we want is the minimum of these variables being less than 1.5. So we have to subtract this from 1, giving us 0.5833. The probability that the minimum of x, y, and z being less than 1.5 is equal to 0.5833, about 58.33%. And then with ChatGPT, you can verify your answer. So I have that here, and you can see final answers confirmed with your results. That's how you solve this problem.